Hello there. Tonight, if you'd like, we're going to visit a quiet library. One that opens only when you close your eyes. Inside, old memories sit on shelves like well-worn books. Some are bright. Some are faded. Some you haven't touched in years. And tonight, you don't need to read any of them. You don't need to remember a single thing. There are quiet librarians who work here. Slow waves, gentle ripples, soft rhythms you'll never hear. And they have been tending to these shelves long before you knew they existed. So if you'd like, just settle in. Let your body rest. Let your mind drift. And let the sound of these pages turning carry you somewhere soft. If you enjoy this kind of gentle company, perhaps you might subscribe. It helps others find their way here too. One sleepy soul at a time. A memory is not a photograph. It is a story the brain retells, slightly differently. Each time, for a long time, people imagined that memories were stored like photographs in a drawer, fixed, crisp, unchanging. But the brain does not work that way. Each time you recall something, the neural pathways reassemble the scene from scattered pieces. The hippocampus coordinates. The cortex supplies details. And the result is never quite identical to the last time you remembered it. The shifts are small, a color slightly warmer, a voice a little softer, but they are always there. Memory, it turns out, is less like a camera and more like a narrator who tells the same story with a slightly different inflection each evening. Perhaps that is a gentle thing, that the stories we carry are alive, still breathing, still becoming. Autobiographical memory weaves facts, feelings, and imagination into a single scene. When you remember a birthday from childhood, you are not retrieving a file. You are weaving together fragments. The smell of candles, the sound of laughter, the feeling of being small in a room full of warmth. Autobiographical memory draws from episodic details, semantic knowledge, and even a quiet thread of imagination to fill the gaps the years have worn away. Researchers describe it as a constructive process. The brain builds the scene each time, rather than playing it back, and the emotional tone of the moment you are in now colors the memory you retrieve. A calm night may soften a memory that felt sharp in daylight. So perhaps the version you remember tonight is the kindest one yet. If you notice any tightness in the jaw, perhaps let it soften, just a little, like a page falling open. Every recall subtly reshapes the memory, like a river carving its banks a little wider each season. Each time you bring a memory to mind, the proteins that hold it together briefly destabilize for a short window, minutes to hours. The memory becomes malleable before it is stored again. Scientists call this reconsolidation. It means that the act of remembering is also, quietly, an act of rewriting. The changes are usually small. A detail smoothed here, an edge softened there. But over many recollections, the memory drifts gently from its original form. This is not a flaw. It may be how the brain keeps old experiences relevant to who you are now, updating them with the quiet wisdom of passing time. Like a river that has traveled the same valley for years, the path is familiar, but the water is always new. The brain stores memories across many regions, not in one drawer, more like books scattered across a house. There is no single memory center in the brain. Instead, different aspects of a memory live in different places. The visual cortex holds what you saw. The auditory cortex keeps the sounds. The amygdala marks the emotional weight. The hippocampus acts as an index, a quiet librarian who knows which shelf holds which fragment. When you recall something, these regions fire together in a coordinated pattern, reassembling the experience from its scattered parts. It is a remarkable act of cooperation. Dozens of neural neighborhoods working in concert, and you never notice any of it happening. Like a house where every room holds a piece of the same story. And somehow, when you walk through, the story tells itself. Episodic memory and semantic memory live in different rooms of the mind. Episodic memory is the kind that carries you back to a specific moment. The afternoon it rained on your walk home. The way the light fell through a kitchen window. Semantic memory, by contrast, holds general knowledge, the name of a city, the meaning of a word, the fact that rain is water. Both are forms of declarative memory, but they are processed and stored through partially different neural circuits. The hippocampus is especially involved in episodic recall, while semantic knowledge can sometimes survive even when the hippocampus is damaged. Over time, some episodic memories lose their vividness and become semantic. The feeling fades, but the knowledge remains, like a dried flower that has lost its scent but kept its shape. Perhaps the shoulders can lower now, as if setting down a photo album you have been holding for a long while. Two people at the same dinner will remember different meals. Memory is shaped by attention, emotion, and perspective, and no two people bring the same combination to the table. One person may remember the laughter, another may remember the silence between conversations. A child at the same gathering might remember only the dessert and the color of the tablecloth. Studies in cognitive psychology consistently show that eyewitness accounts of the same event diverge, not because anyone is lying, but because each brain selected different details to encode. Your memories are not a shared photograph. They are your own quiet painting of the scene, drawn with the colors you happen to notice. And perhaps that is what makes them yours, not their accuracy, but their tenderness. Remembering is a creative act. The brain fills gaps with what feels right. When a memory has missing pieces, and most do, the brain does not leave blanks. Instead, it fills them in with plausible details drawn from other memories, general knowledge, and even imagination. This process, called confabulation in its more extreme forms, is usually so seamless that you never notice it. The result feels complete, feels true, and in a sense, it is true to the version of you who is remembering. Researchers have shown that people can be led to remember events that never happened, simply because the brain constructed a scene that felt coherent. Memory is not a recording. It is a story the mind tells itself, and it tells it with care. Perhaps tonight, the stories can be especially soft. Childhood memories before age 3 are mostly unreachable. Infantile amnesia wraps them in fog. Most people cannot recall events from their first 2 or 3 years of life. This is called infantile amnesia, and it is not because nothing happened. It is because the hippocampus and the neural circuits needed for long-term episodic storage were still maturing. The experiences were real. The laughter was real. The warmth of being held was real. But the filing system was not yet ready to keep them. Some traces may linger as implicit memories, feelings without scenes, comfort without context. But the explicit narratives are gone. It is one of the quieter mysteries of being human, that the very beginning of your story is a chapter you cannot read. And yet, perhaps the warmth of those earliest days still lives somewhere in the body. Unnamed, but present. Memory is not about accuracy. It is about meaning. The brain keeps what it loves most. The brain is not trying to be a perfect archive. It is trying to be a useful one. Over time, memories that carry emotional weight, joy, tenderness, loss, tend to persist, while neutral details fade. This is sometimes called the emotional enhancement effect. The amygdala tags certain experiences as worth keeping, and those tagged memories receive extra consolidation during sleep. The result is a memory landscape shaped not by what happened most often, but by what mattered most deeply. Your brain is, in a sense, a curator, choosing which books to keep on the shelf, which letters to save in the drawer, which photographs to place where you will see them again. And tonight, the curator is resting too, quietly tending to the collection. As it always does, the hippocampus holds new memories, the way a shelf holds recently arrived books. Deep inside the temporal lobe, the hippocampus is a small, curved structure, named after the seahorse it resembles, and it is one of the most studied regions in memory science. New experiences are initially encoded here, bound together as patterns of neural activity, but the hippocampus is not meant to be a permanent home. Over days, weeks, and months, these memories are gradually transferred to the neocortex through a process called systems consolidation. The hippocampus holds the memory while it is fresh, rehearses it during sleep, and then releases it to a wider network for long-term safekeeping. It is a relay station, a temporary shelf, not the library itself, but the place where new arrivals wait to be catalogued. If you'd like, allow the forehead to smooth, as if the mind itself is settling into a quieter arrangement. Over weeks and months, memories travel from the hippocampus to the neocortex for long-term keeping. This journey is called systems consolidation, and it is one of the most elegant processes in the brain. At first, a memory depends heavily on the hippocampus. Without it, the memory would be lost. But gradually, through repeated reactivation during sleep and quiet, waking moments, the memory's neural representation shifts to cortical networks. The neocortex weaves the memory into existing knowledge, giving it context and stability. Some memories complete this journey quickly. Others take months or even years, and some may always retain a thread connected to the hippocampus, a trace of their origin. Like the faint pencil marks a librarian leaves inside a book's cover. The journey is slow, and that slowness may be part of its kindness, giving each memory time to find where it belongs. The prefrontal cortex helps you find the right memory at the right time, a quiet filing system. When you try to remember something specific, where you left your keys, what someone said last Tuesday, The prefrontal cortex is the region that guides the search. It helps you focus retrieval, suppress irrelevant memories, and evaluate whether what you have recalled is accurate. Without it, memories would surface randomly, unbidden, without order. The prefrontal cortex gives memory a sense of direction. It is also one of the last regions to mature in development, which may explain why young children's memories are often vivid but disorganized. The filing system is still being built, and it is one of the first regions affected by fatigue, which is why, after a long day, finding the right memory can feel like searching a dim room. But tonight, there is no searching to do. Everything is already where it needs to be. The amygdala bookmarks memories with emotional weight. A ribbon placed between the pages, sitting just beside the hippocampus. The amygdala is the brain's emotional sentinel. When an experience carries emotional intensity, whether joyful, tender, or painful, the amygdala signals the hippocampus to encode it more deeply. This is why you can remember a single meaningful conversation from years ago, but not what you had for lunch last Wednesday. The amygdala does not store the memory itself. It marks it, tags it, says, "This one matters." During sleep, these tagged memories receive preferential consolidation. The brain spends more time replaying them, strengthening them, giving them a more permanent place. It is a system designed to preserve what moved you. And perhaps, over many nights, the sharp edges of those bookmarked pages soften, until what remains is the warmth, not the ache. Neural pathways that fire together during an event are reactivated during recall. The same chords, replayed. When you experience something, walking through a garden, hearing a familiar song, a specific pattern of neurons fires together. This pattern becomes the memory's neural signature, and when you later recall that experience, a remarkably similar pattern reactivates. Functional imaging studies show that the same brain regions light up during both the original experience and its retrieval. It is as if the brain keeps a musical score and replays it each time you remember, not perfectly, but recognizably. The fidelity of this replay is influenced by how well the memory was consolidated, how emotionally charged it was, and how many times it has been revisited. Maybe let the fingers rest open now, not holding any memory tightly, just letting them be. The chords may change slightly with each playing, but the melody, the feeling, endures. The entorhinal cortex is the gateway, a hallway between the hippocampus and the wider brain. If the hippocampus is a library, the entorhinal cortex is the hallway that leads to its doors. This region processes information from sensory and associative areas and relays it to the hippocampus for encoding. It also carries information back out during retrieval. The entorhinal cortex contains grid cells, neurons that map spatial relationships, and it plays a role in binding where to what in a memory. Without it, the hippocampus would receive fragmented signals. With it, memories arrive with context, the place, the time, the spatial relationship between you and what you experienced. It is a threshold, a quiet doorway through which every memory must pass. And tonight, perhaps the doorway is wide open, letting everything settle softly into place. Place cells map where you were. Your brain remembers the kitchen, The garden, the window. In the 1970s, neuroscientist John O'Keefe discovered that certain hippocampal neurons fire when an animal is in a specific location. He called them place cells. Later research showed that humans have them too. When you walk into a room you have visited before, a unique constellation of place cells activates, creating a spatial map of that environment. These maps become intertwined with memory, so that remembering a childhood home also means remembering its layout. The distance from the door to the window, the way the hallway turned. Place and memory are deeply linked. The brain does not just remember what happened, it remembers where you were standing when it did. Perhaps your body still carries the map of a place that felt like home. Even if the house is long gone, the memory network is not a cabinet. It is a living garden, always growing, always pruning. For decades, the metaphor of memory as storage, filing cabinets, hard drives, vaults, dominated popular imagination. But modern neuroscience paints a more organic picture. Memory networks are constantly changing. New synaptic connections form when you learn. Existing ones strengthen or weaken with use. And unused pathways are pruned away through a process called synaptic homeostasis. The brain is not a warehouse. It is an ecosystem. Memories grow alongside one another, compete for resources, and sometimes merge. The garden metaphor captures something the cabinet metaphor misses. That memory is alive, responsive, seasonal. Some things bloom in spring and fade by winter. Others are perennials, returning year after year, a little different each time. Tonight, the garden rests, the soil is still, and somewhere beneath, the roots hold quietly. Sleep is not passive. The brain is quietly, deeply busy all through the night. From the outside, sleep looks like stillness, but inside the skull, the brain is running one of its most complex operations. Neurons fire in coordinated rhythms. Cerebrospinal fluid washes through the glymphatic system, clearing metabolic waste. Memories are replayed, sorted, and strengthened. Hormones are released on schedule. Body temperature drops. Heart rate slows. And through it all, the brain cycles between distinct stages, each with its own neural signature, its own purpose. Sleep is not the absence of activity. It is a different kind of activity, quieter, deeper, and in many ways, more organized than waking thought. The night shift is always working, and tonight, it has already begun. Whether you notice it or not, the quiet workers are at their stations. Each sleep cycle lasts about 90 minutes, 4 to 6 cycli. Like tides, a full night of sleep is not one long, uniform state. It is a series of cycles, each lasting roughly 90 minutes, and each containing a progression through light sleep, deep sleep, and REM sleep. In a typical night, you may complete 4 to 6 of these cycles. The early cycles are richer in deep sleep, the slow, restorative kind, while later cycles lean more heavily toward REM, the stage associated with vivid dreams. The brain moves through these stages with a rhythm that is ancient and deeply conserved across species. It is not a schedule you need to manage. It happens on its own. The way tides rise and fall without anyone asking them to. Perhaps the chest can soften on the next exhale. Just a little, like a tide going out. Deep sleep is when most memory consolidation gently unfolds. NREM, Stage 3, often called slow wave sleep, is the deepest phase of the sleep cycle. Brainwaves slow to less than 1 cycle per second, and the body enters its most restorative state. It is during this stage that the hippocampus and neocortex engage in their most active dialogue. Memories encoded during the day are replayed in compressed form, transferred gradually from temporary hippocampal storage to more permanent cortical networks. Growth hormone is released. The immune system is supported, and the glymphatic system, the brain's waste clearance pathway, operates most efficiently. Deep sleep is not dramatic. It is not vivid, but it is perhaps the most physiologically productive phase of the entire night, and it asks nothing of you, only that you let go and let the slow waves do their quiet work. The first half of the night is richer in deep sleep. The second half opens the door to dreams. Sleep architecture shifts across the night. In the first 3 or 4 hours, deep NREM sleep dominates. The brain prioritizes consolidation, repair, and physical restoration. As the night progresses, deep sleep episodes grow shorter, and REM periods grow longer. By the final cycle, REM may last 30 to 45 minutes, the longest stretch of the night. This means that if you wake in the early morning, you are more likely to remember a dream. The brain has a kind of internal schedule. First, tend to the body and the memories. Then, open the doors to the rooms where dreams wait. Neither half is more valuable. Both are needed, and both happen without any effort from you. The night has its own rhythm. You are simply invited to rest inside it. When sleep is short, the night librarian simply has less time. But even a brief rest helps. Not everyone gets a full 8 hours. Shift workers, new parents, restless minds. There are many reasons sleep is sometimes cut short. And while longer sleep generally supports better memory consolidation, research shows that even short periods of sleep offer measurable benefits. A 90-minute nap that includes 1 full cycle can strengthen memories. Even a 20-minute nap in the afternoon has been shown to improve alertness and recall. The brain is remarkably efficient. Given even a small window, it begins its work. Replaying, sorting, filing. The night librarian does not refuse to work because the shift is short. The librarian simply does what can be done in the time allowed. So if tonight is shorter than you hoped, perhaps that is enough. The library is patient. A short nap can strengthen a newly formed memory, like pressing a flower between pages. In a study at the University of Lübeck, participants who napped for just 45 minutes after learning a list of word pairs recalled significantly more than those who stayed awake. The nap included spindle-rich NREM sleep, which appeared to stabilize the new memories before they could decay. Other studies have found similar effect. A brief sleep window after learning protects fragile memories from interference and gives the hippocampus a chance to begin its transfer work. The memory does not need hours. Sometimes it needs only a pause, a moment of stillness in which the new trace can harden gently like ink drying on a page. Perhaps rest itself is a form of remembering, a quiet decision to let something settle. The sleeping brain replays the day's experiences, a quiet rehearsal no one hears. During NREM sleep, the hippocampus replays neural patterns that were active during the day, but in compressed form, often 10 to 20 times faster than the original experience. These replays are not random. They tend to prioritize experiences that were novel, emotionally charged, or task-relevant. The replays are thought to gradually teach the neocortex, transferring memories from temporary hippocampal storage to more stable cortical representations. In rodent studies, place cell sequences from daytime exploration are replayed during subsequent sleep. In the same order, but at high speed, the sleeping brain is rehearsing, it is practicing, it is quietly making sure that what happened today finds its place in the larger story. Whenever you are ready, let the belly be soft and unguarded. No effort, no holding. Sleep separates signal from noise, keeping what matters, letting the rest drift. Not everything the brain encodes during the day is worth keeping. Much of it is noise, irrelevant details, passing impressions, background chatter. One of sleep's proposed functions is to help the brain distinguish between signal and noise. Through selective replay and synaptic downscaling, sleep strengthens the memories that matter and allows the rest to fade. This process, sometimes called memory triage, ensures that the brain does not become cluttered with information it does not need. It is a form of editing, not deleting, exactly, but allowing certain impressions to gently recede. The brain is not losing anything of value. It is making space. And perhaps tonight, making space is all that is needed. A quiet clearing, a shelf dusted, a window left open to the cool air. Slow oscillations sweep across the cortex during deep sleep, less than once per second, like a tide. During NREM stage 3, the brain produces large, synchronized waves of electrical activity that ripple across the cortex at a frequency below 1 Hz. These slow oscillations are among the most powerful rhythms the brain generates. They alternate between 2 states: the up state, when neurons are briefly active together, and the down state, when neural activity falls to near silence. This alternation creates a pulsing rhythm that underlies much of what happens during deep sleep. The waves are not random, they are coordinated, traveling across cortical regions in organized patterns. They are the foundation upon which other sleep rhythms, spindles, ripples, are built. Imagine our vast, dark ocean breathing slowly in the night. That is roughly what the sleeping cortex looks like from the inside. These slow waves coordinate the passage of memories between the hippocampus and the neocortex. The slow oscillation is not merely a background rhythm. It serves as a temporal organizer. During the upstate, the hippocampus is signaled to release compressed memory traces, which are then received by cortical networks. The timing is delicate. If the hippocampal output arrives during the down state, it may be lost. The slow wave ensures that transmission happens in a window of receptivity. Researchers have described this as a dialogue between the hippocampus and the neocortex, mediated by the slow oscillation, supported by spindles and ripples. It is a conversation that happens every night, entirely without your awareness. The cortex opens a door, the hippocampus sends a package, and the door closes again. Quietly, all of it happening in the dark, while you simply rest. In the upstate, neurons fire together in a brief, shared chorus. The upstate of the slow oscillation is a moment of synchronized activation across wide areas of the cortex. Neurons fire in concert. A brief, collective burst of activity lasting a few hundred milliseconds. During this window, the brain is maximally receptive to incoming signals from the hippocampus and thalamus. It is also during the upstate that sleep spindles are most likely to occur, nesting within the wave like a smaller rhythm held inside a larger one. The upstate is thought to facilitate the integration of new memories into existing cortical networks. It is a moment of openness, a brief inhale in the breathing rhythm of the sleeping brain. You might feel the feet growing warmer now, heavier, as if they have found exactly where they want to be. And then the brain exhales, and the down state returns. A whoosh, deep and complete. In the down state, the brain falls into a collective hush, a breath held gently. If the up state is the inhale, the down state is the exhale, or perhaps the pause between breaths. During the down state, cortical neurons fall silent almost simultaneously. This is not damage or dysfunction. It is a coordinated rest. The silence may serve a purpose. It allows synapses to reset, clears residual activity, and prepares the cortex for the next up state. Some researchers believe the down state also plays a role in synaptic homeostasis, the process by which the brain scales down overall synaptic strength during sleep, preventing the neural network from becoming saturated. It is a form of maintenance, the brain tidying its workspace before the next wave arrives. A silence that is not empty, but purposeful, like the space between notes that makes the music whole. After a day of learning something new, slow wave sleep increases. The brain asks for more time. The brain is responsive to its own needs. After intensive learning, studying a new language, navigating an unfamiliar city, practicing a musical passage, the amount of slow-wave sleep in the following night tends to increase. This has been observed in both laboratory studies and naturalistic settings. The increase appears to be localized. If you learned a motor task with your right hand, the left motor cortex, which controls the right hand, may show enhanced slow-wave activity during sleep. The brain does not simply run a fixed program each night. It adjusts, allocates, responds to what happened during the day. It gives more time to the areas that worked hardest. Like a gardener who lingers a little longer at the beds that were newly planted, knowing they need extra care to take root. The strength of these waves in the morning correlates with how well memories hold. Studies have shown that the intensity of slow-wave activity during the night, measured by the amplitude and density of slow oscillations, predicts memory performance the following day. Participants who show stronger, slow waves after learning tend to recall more accurately in the morning. This correlation has been found for declarative memories, facts and events, procedural memories, skills, and even emotional memories. Some researchers have experimented with boosting slow waves artificially, using gentle auditory tones timed to the rhythm, and found that this can enhance memory consolidation. The slow wave is not just a sign of deep sleep, it appears to be a functional tool that the brain uses to strengthen what it has learned. The deeper the wave, the more firmly the memory is held, like a stone settled at the bottom of a still pond. Some researchers call them the breathing rhythm of the sleeping brain. The analogy is apt. Just as breathing is rhythmic, automatics, and life-sustaining, the slow oscillation represents the brain's own respiratory cycle during sleep. It rises, falls, rises again, each cycle bringing a moment of activity followed by a moment of rest. And like breathing, it is not something you control. It happens beneath awareness, driven by the intrinsic properties of cortical neurons and their connections. The rhythm is ancient, observed in mammals across species, from mice to whales, and it likely evolved because it serves a deep biological need, the need to process, to prune, to prepare the brain for another day. Each slow wave is a breath the brain takes for itself. And tonight, the brain is breathing steadily. No rush, no hurry, just the calm pulse of the deep dark. As we grow older, slow wave sleep shortens, but it does not fully leave. One of the most consistent findings in sleep research is that slow wave sleep declines with age. By middle adulthood, the amplitude of slow oscillations is typically lower than in young adults, and the total time spent in NREM stage 3 decreases. Some researchers have linked this decline to age-related changes in memory consolidation, but the decline is gradual, not absolute. Even in older adults, slow waves persist. They are smaller, perhaps, but they are still there, still doing their work. The brain adapts. It finds ways to consolidate with the resources it has, and some studies suggest that maintaining good sleep hygiene can preserve slow-wave sleep longer into life. Perhaps the eyelids can be gently weighted now, like dusk settling over a quiet field. The waves may be smaller, but they are no less faithful. Sharp wave ripples are brief bursts in the hippocampus during NREM, tiny flashes in the dark. While the cortex breathes its slow rhythm, the hippocampus generates its own distinct pattern, sharp wave ripples. These are brief, high-frequency bursts of neural activity. A sudden spike followed by a fast oscillation, all compressed into a fraction of a second. They occur spontaneously during NREM sleep and quiet wakefulness. Each ripple represents a compressed replay of a recent experience, a condensed version of what happened during the day, fired off at extraordinary speed. The ripple is not loud. It is not dramatic. It is a whisper in the neural dark, quick, precise, and remarkably efficient, like a firefly blinking once in a wide, dark field. Brief, but carrying a message only the night can read. Each ripple lasts 50 to 100 milliseconds, faster than a blink, quieter than a whisper. The timescale of a sharp wave ripple is almost inconceivably brief. In the span of 50 to 100 milliseconds, less time than it takes to blink, the hippocampus fires a coordinated burst that encodes a compressed version of an entire experience. The internal oscillation within the ripple runs at 150 to 250 Hz, making it one of the fastest rhythms in the brain. Despite their brevity, these ripples carry dense information. They are thought to be the primary vehicle by which the hippocampus communicates with the neocortex during sleep. Thousands of ripples occur in a single night. Each one, a tiny package of compressed experience being sent along the neural mail route. So much happens in a fraction of a second, and all of it while you are perfectly, beautifully still. During a ripple, the hippocampus replays compressed versions of what happened during the day. The content of a sharp wave ripple is not random. Studies in rodents have shown that the sequences of place cells activated during daytime exploration are replayed during ripples, in the same order, but at 10 to 20 times the original speed. This suggests that the hippocampus is running through the day's events in fast forward, distilling each experience into its essential neural pattern. The replays tend to prioritize recent and emotionally salient experiences, though older memories can also be reactivated. Each ripple is a miniature retelling, the brain's way of rehearsing a story so many times that the cortex learns it by heart. A story told so quickly that only the sleeping brain can hear it. And yet, the cortex remembers every word. These replays run 10 to 20 times faster than the original. A story told in shorthand. Time compression is one of the most striking features of hippocampal replay. An experience that took several seconds to unfold is replayed in tens of milliseconds. This compression is not random. It preserves the temporal order of the original experience, while dramatically accelerating it. The result is a kind of neural shorthand, the essence of the experience, stripped of real-time duration. Researchers believe this compression may be necessary for efficient communication with the neocortex, which operates on different timescales. The hippocampus speaks quickly, the cortex listens slowly, and somehow, in the dark of sleep, they understand each other perfectly, like a letter written in tiny script on a single page, containing everything that matters, with nothing wasted. Ripples may teach the neocortex, transferring memories gradually, night after night. The relationship between hippocampal ripples and cortical consolidation is thought to be instructive. The hippocampus teaches the neocortex through repeated exposure. Each night, the same memory may be replayed dozens of times during ripples. And, with each replay, the cortical representation grows a little stronger. Over days and weeks, the memory becomes less dependent on the hippocampus and more firmly embedded in cortical networks. This gradual transfer is what allows old memories to survive even when the hippocampus is damaged. The teaching is patient. It does not happen in one night. It happens across many nights, each one adding a layer to the cortical trace, like a teacher who repeats a lesson softly, knowing that understanding comes not from force, but from gentle repetition. Ripples often align with slow waves and spindles, a coordinated trio working in the dark. The most effective memory consolidation appears to occur when three rhythms align: the slow oscillation, the sleep spindle, and the sharp wave ripple. During the upstate of the slow oscillation, the thalamus generates a spindle. Nested within that spindle, the hippocampus fires a ripple. This precise temporal coupling creates a window of optimal plasticity, a moment when the cortex is maximally receptive to new information. Studies have shown that memories consolidated during periods of strong coupling are retained better than those processed during poorly aligned events. The trio works in concert, each rhythm supporting the others. Let the fingertips loosen now. releasing the small effort of remembering, letting the hands rest as if they have set down a pen. 3 rhythms, 1 purpose, and all of it happening while you do nothing at all. In studies, disrupting these ripples impairs memory. The librarian needs silence. Some of the strongest evidence for the role of sharp wave ripples in memory comes from disruption experiments. In rodent studies, selectively suppressing ripples during sleep, using electrical stimulation triggered by real-time detection, impairs the animal's ability to remember spatial tasks learned before sleep. The more ripples are suppressed, the worse the memory performance. These findings suggest that ripples are not merely correlated with consolidation. They are causally involved. The hippocampus needs these quiet bursts to do its work. Interrupt them, and the transfer fails. The message does not reach its destination. The night librarian works best in silence. Not because silence is empty, but because it is the medium through which the quiet work is done. Ripples appear more often after emotionally meaningful or novel experiences. The hippocampus does not replay everything equally. Experiences that were emotionally charged, whether joyful, surprising, or tender, tend to generate more ripples during subsequent sleep. Novel experiences, too, are replayed more frequently. This selectivity aligns with behavioral findings. Emotional and novel memories are generally better remembered than routine ones. The amygdala may play a role here, signaling the hippocampus to prioritize certain traces for replay. The result is a form of emotional triage. The brain gives more rehearsal time to the experiences that mattered most. It is not a conscious choice. It is a biological inclination toward preserving what moved you. The ripples come more often for the memories that touched something deeper, as if the brain knows, without being told, what is worth keeping close. Sleep spindles pulse at 7 to 14 times per second, generated by the thalamus, a sentinel of sleep. The thalamus sits deep in the center of the brain, serving as a relay station between sensory systems and the cortex. During wakefulness, it transmits sensory information. During sleep, it shifts into a different mode. It generates rhythmic bursts of activity called sleep spindles. These oscillations range from 7 to 14 Hz, sigma frequency, and they sweep across the cortex in brief, waxing and waning bursts. The thalamus, in sleep, becomes less a messenger and more a musician, producing a rhythm that the cortex uses for its own internal work. It is a transformation that happens every night. The brain's switchboard becomes the brain's metronome, a quiet sentinel, keeping time in the dark, so the rest of the brain can work in rhythm. Each spindle lasts about half a second to 2 seconds, a soft chime in the neural dark. A sleep spindle is brief but structured. It begins with a crescendo of oscillatory activity, peaks in amplitude, and then feathers, a waxing and waning envelope that lasts roughly 0.5 to 2 seconds. The shape is distinctive on an EEG, recording a small, symmetric burst nestled within the broader landscape of slow-wave sleep. Hundreds of spindles occur in a single night, each one a discrete event with its own timing and cortical distribution. Some spindles are frontal, slow spindles. Others are centroparietal, fast spindles, and they may serve slightly different functions. but all share the same basic form, a brief, self-contained pulse of organized activity, a chime that rings once, softly, and then is gone, leaving only its echo in the cortical tissue it touched. Spindles may help gate information into cortical storage, opening a small door, then closing it. One of the leading theories about sleep spindles is that they create brief windows of enhanced plasticity in the cortex. During a spindle, the rhythmic inhibition and excitation of cortical neurons may facilitate the long-term potentiation of synaptic connections. The cellular mechanism underlying memory storage, in other words, the spindle opens a gate for a fraction of a second. The cortex is especially receptive to incoming information. When a hippocampal ripple arrives during this window, the memory trace may be stamped more firmly into cortical tissue. The gate then closes, and the cortex returns to its resting rhythm. Maybe the space between the brows can widen now, releasing any small tension you did not know you were holding. A door that opens and closes so gently, you would not hear it, but the memory slips through. People with higher spindle density tend to show stronger memory performance the next day. Across numerous studies, individual differences in spindle density, the number of spindles per minute of NREM sleep, have been correlated with memory performance. People who produce more spindles tend to remember more of what they learned before sleep. This relationship holds for word lists, spatial tasks, motor skills, and even emotional memories. Some researchers have found that spindle density increases on nights after intensive learning, suggesting that the brain upregulates spindle production when there is more to consolidate. Spindle density also varies with age and is generally higher in individuals with stronger cognitive abilities. It is one of the more reliable neural biomarkers of sleep-dependent memory. The brain that chimes more often may simply be keeping more cut, like a librarian who stamps each book with extra care. Spindles often nest inside the upstate of slow waves, a rhythm cradled within a rhythm. The temporal relationship between spindles and slow oscillations is precise and functionally meaningful. Spindles tend to occur during the upstate of the slow oscillation, the moment when cortical neurons are active and receptive. This nesting creates a hierarchical structure. The slow wave provides the broadest temporal frame. The spindle sits within it, and the hippocampal ripple may nest within the spindle itself. This triple nesting, slow oscillation, spindle, ripple, is thought to be the optimal configuration for memory transfer. It is an architecture of extraordinary precision, assembled and disassembled thousands of times each night, entirely without your knowledge. A rhythm held inside a rhythm, held inside another, like a lullaby heard from several rooms away, each wall softening the sound a little more. The coupling of spindles and ripples may be how memories are gently archived. When a hippocampal ripple coincides with a cortical spindle, the probability that the associated memory will be retained increases. This spindle-ripple coupling has become a focus of memory research because it appears to represent the moment of transfer, the instant when a memory moves from temporary hippocampal storage to more permanent cortical residence. Studies using intracranial electrodes in humans have confirmed that memories associated with stronger coupling are better remembered the next day. The coupling is not guaranteed. Not every ripple finds a spindle. Not every spindle carries a memory. But when the timing aligns, something quiet and consequential happens. The archive grows, one gently filed page at a time, and the night continues its unhurried work. After learning, spindle activity increases. The brain quietly rehearses what it just received. The brain responds to learning by adjusting its sleep architecture after a day of intensive cognitive activity, memorizing vocabulary, studying maps, practicing a musical piece. The subsequent night's sleep tends to show increased spindle activity. This increase is not global. It is often localized to the cortical areas most involved in the learning task. If you practiced a motor skill with your left hand, spindle density may rise selectively over the right motor cortex. This specificity suggests that spindles are not merely a sign of good sleep. They are a targeted response to learning, directed by the brain to the regions that need it most. The brain does not waste its quiet hours. It uses them specifically, precisely, and with a tenderness that no one sees. Spindles appear in infancy and grow more organized with age. The library expands. Sleep spindles are present from the earliest months of life, though they are initially irregular and poorly defined. As the brain matures, spindles become more organized, their frequency stabilizes, their amplitude increases, and their distribution across the scalp becomes more consistent. By adolescence, spindle architecture closely resembles that of adults. This developmental trajectory parallels the maturation of memory systems, suggesting that spindles and memory grow together. In infants, spindles may support the rapid learning that characterizes early life, the acquisition of language, motor skills, social understanding. The spindle system is not static. It is a developing tool, refined over years. You might let the thighs sink into whatever supports them now. No effort needed, just a quiet settling. The library was small once. It has been growing all your life. The thalamic reticular nucleus orchestrates when spindles begin and end. Acquiet conductor. The generation of sleep spindles depends on a thin sheet of inhibitory neurons called the thalamic reticular nucleus. These neurons inhibit the relay cells of the thalamus in a rhythmic pattern, creating the characteristic waxing and waning spindle oscillation. The reticular nucleus acts as a pacemaker, initiating the spindle, sustaining it for a brief period, and then allowing it to decay. The precision of this process is remarkable. The reticular nucleus must balance excitation and inhibition with exquisite timing to produce a spindle of the right frequency and duration. It is a conductor's role, setting the tempo, cueing the instruments, and knowing exactly when to let the music fade. A conductor no one sees, leading an orchestra no one hears. And yet, the music plays on, every single night. REM, sleep, brings rapid eye movements, vivid dreams, and a body at rest. Muscle, atonia, keeps you still. During REM sleep, the brain becomes remarkably active, almost as active as during waking. The eyes move quickly beneath closed lids. Brain waves shift to low amplitude, high-frequency patterns that resemble alertness, and yet, the body is deeply still. A mechanism called muscle atonia, mediated by the brainstem, suppresses voluntary muscle movement, preventing you from acting out your dreams. Only the diaphragm and the eye muscles are spared. REM typically appears 90 minutes after sleep onset and grows longer in later cycles. It is the stage most associated with vivid, narrative dreaming, the stage where the brain seems to be telling itself stories in the dark. And while the body rests, perfectly still, the mind travels, softly, freely, without any weight to carry. REM is proposed to soften the emotional charge of memories, a quiet, dimmer switch. One of the most intriguing theories about REM sleep is that it helps reduce the emotional intensity of memories while preserving their content. The idea, proposed by sleep researcher Matthew Walker and others, suggests that during REM, the brain replays emotional experiences in a neurochemical environment that is low in norepinephrine, the stress-related neurotransmitter. This allows the memory to be processed without the accompanying emotional arousal over successive nights. The emotional charge of the memory may gradually diminish, leaving the factual content intact but the feelings softer. It is not erasing. It is not forgetting. It is more like turning down a volume dial until the sound is still audible but no longer overwhelming. A dimmer switch for the heart, lowered gently, night by night, until the light is warm instead of blinding. After REM-rich sleep, people often rate emotional images as less distressing the next morning. In laboratory studies, participants who viewed emotionally charged images and then slept with REM sleep intact rated those same images as less upsetting the next day, compared to participants who stayed awake for the same duration. The memory of the image remained, but the emotional response was muted. Brain imaging showed reduced amygdala reactivity to the images after sleep, suggesting that the brain's emotional center had recalibrated overnight. This effect appears to depend specifically on REM. When REM is disrupted, the emotional response persists at its original intensity. The implication is that REM sleep serves a kind of emotional housekeeping, gently recalibrating reactions so that old feelings do not dominate the present. By morning, the scene is the same, but the feeling has been softened, as if seen through a window washed by rain. The prefrontal cortex quiets during REM, allowing emotions to be processed without the usual guard. During waking life, the prefrontal cortex helps regulate emotions, suppressing impulses, reframing thoughts, maintaining composure. But during REM sleep, prefrontal activity drops significantly. This reduced oversight may actually be beneficial for emotional processing. Without the prefrontal guard, the brain can engage with emotional memories more directly, allowing them to be reprocessed in a way that would be difficult while awake. This may explain why dreams are often emotionally vivid and logically disjointed. The emotional brain is active, but the rational brain is resting. The result is a kind of unguarded processing, the brain working through feelings without the filters it normally applies. Perhaps the arms can feel pleasantly distant now, as if they belong to someone who is already asleep. Sometimes the guard needs to rest, too, and in that rest, something heals. Dream content draws from both recent and distant memories, fragments drifting together. Dreams are not simple replays. They are collages. A face from childhood may appear in a room from last week. A feeling from years ago may attach itself to a scene from yesterday, Research shows that dream content incorporates both recent experiences, the day residue effect, and older memories, often combining them in novel and unexpected ways. This blending may serve a function by juxtaposing old and new. The brain may be testing connections, integrating recent experiences into the broader web of long-term memory. The dream does not need to make logical sense. Its purpose may be associative, finding links between experiences that the waking mind would never combine, fragments drifting together in the dark, not random, but searching for where they fit. After emotionally heavy days, REM sleep tends to increase. The brain asks for more dreaming, just as slow-wave sleep increases after intensive learning. REM sleep appears to increase after emotionally demanding days. Studies have found that participants exposed to stressful or emotional experiences show longer and more frequent REM episodes in subsequent sleep. The brain seems to recognize when there is more emotional material to process and allocates additional REM time accordingly. This adaptive response is consistent with the theory that REM serves an emotional regulatory function. The heavier the day, the more time the brain devotes to softening its edges during the night. It is not a conscious decision. It is a biological kindness. The brain caring for itself the only way it knows how. If today was heavy, perhaps tonight the dreaming will be a little longer and a little kinder. Low norepinephrine during REM may allow the brain to replay memories without retriggering stress. Norepinephrine is a neurotransmitter associated with alertness, arousal, and the stress response. During REM sleep, norepinephrine levels drop to their lowest point of the entire day, effectively creating a neurochemical environment in which emotional memories can be reactivated without triggering the fight-or-flight response. This is thought to be one of the key mechanisms by which REM helps to dissociate memory content from emotional reactivity. The brain can practice the memory, replay the scene, feel the echo of the emotion, without the full physiological cascade that would occur while awake. It is a kind of safe rehearsal. The story plays, but the body remains calm. The memory arrives, but the alarm does not sound, and slowly, the memory learns that it is safe to be remembered. REM may help weave emotional memories into broader life stories, giving them a gentler context. Beyond reducing emotional intensity, REM sleep may also help integrate emotional experiences into the larger narrative of a person's life. By associating recent emotional memories with older, more processed ones, the brain may provide context that reduces the raw impact of the experience. A painful event, once isolated, may become connected to other times of difficulty and recovery, placing it within a larger arc that includes resilience. This narrative integration is still being studied, but it offers an appealing framework. REM does not just soften the feeling, it gives the feeling a place in the story. If the jaw has tightened again, perhaps let it release, softer than before, like a second chapter that is gentler than the first. The feeling does not disappear. It finds a room where it can sit quietly, beside other feelings that came before. Not all softening happens in REM. NREM helps too, but in its own quiet way. While REM has received the most attention for emotional processing, NREM sleep also contributes. Slow-wave sleep supports the consolidation of emotional memories and the coordination of slow oscillations. Spindles and ripples appears to stabilize emotional traces alongside declarative ones. Some studies suggest that NREM may help with the factual component of emotional memories, the what happened, while REM addresses the how it felt. The two stages may work in tandem. NREM stabilizes the memory's structure, and REM softens its emotional tone. Neither does the job alone. Together, they offer a complete process, one that unfolds gradually across every cycle of the night. Two workers in the same quiet room, one shelving books, the other dimming lights, and the room grows more peaceful with each pass. When a memory is recalled, it briefly becomes malleable, a window called reconsolidation. For decades, scientists believed that once a memory was consolidated, it was fixed, stored permanently in its original form. But research in the early 2000s revealed something remarkable. When a memory is actively recalled, it temporarily destabilizes. The proteins holding the synaptic connections in place partially degrade, and the memory enters a labile state. During this window, lasting minutes to hours, the memory can be modified before being restabilized. This process is called reconsolidation. It means that every act of remembering is also an act of updating. The memory you retrieve is not identical to the one you stored. It is the latest draft, shaped by who you are now, not just who you were then. A window opens briefly, the air changes, and when it closes, the room is a little different than before. During this window, the memory can be updated with new feelings or a different frame. The reconsolidation window is not just a vulnerability, it is an opportunity. If new information or a new emotional state is present during recall, it can be incorporated into the memory as it is restabilized. Therapeutic approaches have begun to explore this imagery. Rescripting, for example, asks a person to recall a distressing memory and then imagine an alternative outcome. If the memory is reconsolidated with this new frame, the distress may diminish. The memory itself is not erased. The events remain, but the emotional coloring shifts. It is as if the same photograph is reprinted on different paper. The image is the same, but the texture, the warmth, the feeling of holding it has changed. The past cannot be rewritten, but perhaps the way we hold it can be softened. Sleep after reconsolidation may help save the kinder version of the memory. If a memory is recalled and then gently reframed, the subsequent sleep may help stabilize the updated version. Research has shown that sleep after reconsolidation can enhance the incorporation of new emotional associations. In one study, participants who napped after imagery, rescripting of a distressing autobiographical memory, showed reduced emotional reactivity compared to those who stayed awake. The nap appeared to consolidate the kinder version of the memory, making it more durable. Sleep, in this context, acts as a gentle seal, closing the reconsolidation window with the updated version inside. Maybe the shoulders can settle now, like closing book covers at the end of a revised chapter. The old version is not gone, but the version the brain keeps closest may be the one that hurts the least. Spindle density during that nap correlated with a greater drop in heart rate reactivity. In the same nap study, researchers measured sleep architecture and found that participants with higher central sleep spindle density during the nap showed a greater reduction in heart rate response to the distressing memory. This suggests that spindles may play a direct role in the reconsolidation process, not just consolidating factual content, but helping to restabilize the memory with its new, softer emotional tone. The finding is still preliminary. A single study, a small sample, but it is consistent with the broader picture. Spindles are not merely signs of good sleep. They are active agents in the brain's effort to process, soften, and refile what has been felt. The quiet chime of the spindle, working even on the memories that ache, gently, patiently, one oscillation at a time. Reconsolidation is not erasing. It is editing a draft with softer words. The language of reconsolidation can be misleading. It is not deletion. The original experience remains in some form. The brain does not erase events. What changes is the way the memory is held, the emotional weight, the interpretive frame, the physiological response it triggers. A memory that once brought a sharp pang may, after many cycles of reconsolidation, bring only a dull warmth. The facts are the same. The story is the same. But the words have been quietly revised. A harsher phrase replaced with a gentler one. An accusatory sentence softened into an observation. The brain is not a perfect editor, but it is a persistent one. Draft after draft, night after night, and slowly, the story becomes one you can hold without flinching. The window stays open for a few hours after recall. Then the memory settles again. The reconsolidation window is time-limited. After a memory is recalled and enters its labile state, it remains modifiable for a period that researchers estimate ranges from a few minutes to several hours. After this window closes, the memory is restabilized, either in its original form or in an updated one. Depending on what happened during the window, the brain then requires new protein synthesis to lock the memory back into place. This is why sleep, shortly after emotional processing, may be particularly beneficial. The reconsolidation window is still open, and sleep provides the neurochemical environment needed to stabilize the revised trace. The window does not stay open forever. But tonight, if it opened at some point today, sleep may be the kindest way to close it. This may explain why old memories feel different over time. They are being quietly rewritten. Have you ever noticed that a memory from years ago feels different than it once did? The scene is the same, but the emotion has shifted. What once felt like grief may now feel like tenderness. What once felt urgent may now feel distant. Reconsolidation offers a possible explanation each time you recall that memory. It was briefly destabilized and then restored, sometimes with subtle updates. Over many cycles of recall and reconsolidation, the memory drifts. It softens. It becomes less about the event itself and more about the meaning you have given it. The brain is not rewriting history. It is rewriting the feeling, one recall at a time. And perhaps that is how old wounds become old wisdom. Slowly, quietly, without anyone noticing the change. Nostalgia was once considered a disease. Swiss soldiers were diagnosed with it in the 1600s. The word nostalgia was coined in 1688 by a Swiss medical student named Johannes Hofer. He combined two Greek roots, Nostos, meaning homecoming, and algus, meaning pain, to describe a condition he observed in Swiss mercenaries stationed far from home. These soldiers experienced sadness, insomnia, loss of appetite, and even favor. For centuries, nostalgia was treated as a medical disorder, a disease of excessive longing. It was only in the late 20th century that psychologists began to reconsider it as a normal emotional experience, common across cultures and ages. Today, nostalgia is understood not as an illness, but as a complex emotion, one that can carry both comfort and ache. If you would like, let the forehead smooth, as if the mind is setting down a very old word it has been carrying, a word born from pain, slowly reimagined as something softer. Today, psychology sees nostalgia as a mixed emotion, warm at its center, bittersweet at its edges. Modern research on nostalgia describes it as a self-conscious, social emotion that involves fond remembering of the past, often tinged with a sense of loss. It is not purely positive and not purely negative. It is both. In controlled experiments, nostalgia has been associated with increased feelings of meaning, social connectedness, and self-continuity, but it also reliably evokes a sense of longing, an awareness that what is remembered is gone. This duality is what makes nostalgia so distinctive. It can warm you and wound you in the same breath, and neither response is wrong. Both are real. Both are valid. A guest who arrives carrying flowers in one hand and rain in the other, and you welcome them because they are telling the truth. In lapse, guided nostalgia often lifts, meaning self-worth and a sense of connection. When researchers ask participants to recall a nostalgic memory in a controlled setting, the results are generally positive. People report heightened feelings of existential meaning, stronger self-esteem, and a greater sense of social belonging. These effects have been replicated across multiple studies and cultures. Nostalgia, in the laboratory, functions as a psychological resource, a way of drawing warmth from the past to nourish the present. The memories people choose to recall tend to feature loved ones, shared experiences, and moments of connection. This may be why the effects are so reliably positive in the lab. People select their warmest memories. But the lab is not the bedroom at midnight, and the memory that arrives unbidden may carry a different weight. But in daily life, naturally, arising nostalgia can sometimes walk in with sadness beside it. Outside the laboratory, nostalgia does not always follow the same script. Daily diary studies have found that when nostalgia arises naturally, on ordinary days, in ordinary moments, it is more likely to be accompanied by negative affect than when it is prompted in a lab. The difference may be one of context in the lab. You choose what to remember. In life, the memory chooses you, and it may arrive at an inconvenient hour, when defenses are low and loneliness is near. Natural nostalgia is not always warm. Sometimes it is heavy. Sometimes it sits beside sadness and says nothing at all. And if that happens tonight, if a memory arrives with an ache, perhaps you can let it be there without judging it, and without asking it to leave. The difference may be context lab-prompted nostalgia is tidy. Real-life nostalgia arrives uninvited. Researchers have begun to explore why nostalgia's effects differ between lab and life. One explanation is selection bias in experiments. Participants are asked to recall a specific nostalgic memory, and they typically choose one that is manageable and warm. In daily life, nostalgia may be triggered by a song on the radio, a scent, a photograph stumbled upon the say, triggers that are not curated and may activate memories that are more complex, more painful, more layered. The emotional outcome depends not just on the memory itself, but on the state of the person experiencing it. Context is everything. The same memory, recalled on a good day and a bad day, may feel like two entirely different visits. Some visitors knock, others let themselves in, and the room is not always ready. Nostalgic memories almost always feature other people. Nostalgia is inherently social. Content analyses of nostalgic memories consistently show that the self is rarely alone. Almost every nostalgic memory involves other people, friends, family members, romantic partners, communities. Nostalgia, at its core, is about connection. It is the ache of remembering togetherness that has passed. This social dimension may explain why nostalgia can strengthen feelings of belonging by revisiting moments of connection. The brain briefly reactivates the sense of being held, of mattering to someone, but it also explains the ache. The people in the memory may no longer be present, or the relationship may have changed. Nostalgia always points to others, and through them, to the version of yourself that existed in their company. You are not remembering a place. You are remembering who you were when you were not alone. The most nostalgic memories cluster around ages 15 to 25. The reminiscence bump. When older adults are asked to recall memories from their lives, a disproportionate number come from adolescence and early adulthood, roughly ages 15 to 25. This phenomenon is called the reminiscence bump. It is thought to occur because this period is rich in novel, identity-forming experiences. First love, leaving home, forming beliefs, discovering who you are. These memories are encoded with particular strength. They are emotionally charged, personally meaningful, and frequently rehearsed. They become the core chapters of the life story. The reminiscence bump is not unique to nostalgia, but it helps explain why nostalgic memories so often feel vivid and significant. They come from the years when the self was being written for the first time. The years that shaped you most, shelved with extra care, returned to more often than any others. Music is perhaps the most reliable key to the nostalgia door. Of all the triggers of nostalgia, music is the most consistent and the most powerful. A song heard decades ago can instantly transport you to a specific time, a specific feeling, a specific room. This is because music is processed through multiple brain regions simultaneously: auditory cortex, limbic system, prefrontal cortex, and becomes deeply intertwined with emotional memory. Music-evoked autobiographical memories are often more vivid, more emotional, and more specifically located in time than other cued memories. Even in individuals with severe memory impairment, music can sometimes unlock memories that are otherwise inaccessible. It is a key that fits many doors. Maybe let the palms open gently now, as if you are holding a melody you once loved and letting it play. The song remembers you, Even when you have forgotten the song, nostalgia can make the present feel warmer, or it can make the present feel further away. The dual nature of nostalgia extends to its relationship with the present moment. For some people, in some contexts, recalling a warm memory makes the present feel brighter, a borrowed glow from the past. For others, the contrast between then and now can make the present feel emptier. Research suggests that the direction of the effect depends on individual factors: attachment security, current mood, social context, and on the specific memory recalled. There is no universal rule. Nostalgia is not a medicine with a predictable dose. It is a visitor whose effect depends entirely on the room it walks into. Some nights it warms you. Some nights it just sits there, saying nothing. And both are perfectly natural parts of being human. On lonelier days, nostalgia's bittersweet edge grows sharper. The warmth cools faster. Research using daily diary methods has found that nostalgia experienced on days when loneliness is high tends to carry more negative affect than nostalgia experienced on days when loneliness is low. The same emotion, the same fond remembering, feels different depending on the emotional landscape it arrives in. On connected days, nostalgia may reinforce warmth. On lonely days, it may highlight absence. The interaction between nostalgia and loneliness is not simple, and it challenges the popular idea that nostalgia is always a comfort. Sometimes it is. Sometimes it magnifies the very feeling it seems to be trying to soothe. The warmth is still there, but on lonelier nights, it cools a little faster, like a cup of tea left too long beside an open window. 5 diary studies found that nostalgia and loneliness together predicted lower positive mood. Across 5 separate diary studies involving over 500 participants, researchers found a consistent pattern on days when both nostalgia and loneliness were elevated. Positive affect was lower than on days when either emotion appeared alone. The effect was interactive. It was not simply that loneliness was bad for mood, but that loneliness changed the way nostalgia functioned. Instead of lifting spirits, nostalgia, in the presence of loneliness, appeared to deepen the ache. The findings suggest that nostalgia's emotional impact is context-dependent, shaped not only by what you remember, but by how you feel when you remember it. The same rain falls differently on different soil. And tonight, whatever the soil, it is enough to just be here. Loneliness may shift nostalgia from fond remembering to aching comparison. When you are feeling connected and secure, a nostalgic memory can feel like a gift, a reminder that you have been loved, that you have belonged. But when you are feeling lonely, the same memory can become a mirror that reflects what is missing. Instead of "I was happy then," the thought becomes, "I am not happy now." This shift from fond remembering to painful comparison may explain why nostalgia's effects are so variable. The memory itself has not changed. The frame has. Loneliness narrows the frame, focusing it on absence rather than presence. The brain is not being cruel. It is simply responding to the emotional context it finds itself in. And perhaps that is why gentleness toward yourself on lonely nights matters more than any particular memory. People who feel more secure in their attachments tend to find more comfort in nostalgic memories. Attachment theory offers one lens for understanding why nostalgia affects people differently. Research suggests that individuals with secure attachment styles, those who feel fundamentally safe in their relationships, are more likely to experience nostalgia as comforting and mood-repairing. Individuals with insecure attachment styles, particularly those high in attachment anxiety, may find nostalgia more distressing. The warm memory triggers not just fondness, but also fear of loss. The same memory of being held can feel like a blessing or a reminder of fragility. Depending on the listener's inner landscape, perhaps the chest can soften here, not to fix anything, just to make a little more room for whatever is being felt. The comfort is not in the memory, it is in the feeling of safety you bring to it. For others, nostalgia can sometimes amplify the ache of what is missing. Not everyone finds solace in looking back. For some, nostalgic memories intensify the gap between past and present, making the then feel brighter and the now feel dimmer by comparison. This is especially true when the nostalgic memory involves someone who is no longer accessible through death, distance, or the quiet dissolution of a relationship. In these cases, the memory does not soothe, it sharpens, and the response is not a sign of weakness or dysfunction. It is a sign that the connection mattered deeply. The ache is proportional to the love, and perhaps the kindest thing to do with that ache is simply to acknowledge it, not to push it away, not to amplify it, but to let it sit where it is. Some aches are just love with nowhere to go, and that, too, deserves a place to rest. The effect of nostalgia on well-being depends on the soil it lands in, the context of that night. Researchers have increasingly recognized that nostalgia is not a single-effect emotion. Its impact on well-being depends on a constellation of factors: the person's current mood, their attachment style, whether they are alone or with others, the specific memory recalled, and the triggers that activated it. This contextual sensitivity makes nostalgia one of the most complex emotions studied in affective science. It resists simple labels. It is not good or bad. It is responsive, shaped by the conditions it encounters. The same seed planted in different soil will produce different fruit, and on any given night, the soil is what it is. You do not need to control what you feel tonight. You only need to be gentle with whatever arrives. Shared nostalgia with others is generally warmer than solitary nostalgia. When people engage in nostalgia together, sharing old stories, looking at photographs, reminiscing about a shared past, the emotional outcome tends to be more positive than when nostalgia is experienced alone. Shared reminiscence activates social bonding pathways and reinforces the sense of belonging that nostalgia naturally evokes. The presence of another person provides a container for the emotion, someone to validate the memory, to laugh or sigh alongside you. Solitary nostalgia lacks this container. The memory arrives, and there is no one to catch it with you. This may be one reason why nostalgia on lonely nights is harder. It is not just the loneliness, it is the absence of a witness. But tonight, perhaps this voice can be a kind of company, quiet, unhurried, asking nothing in return. Social media can trigger nostalgia, but the evidence on whether it helps is mixed. Platforms that surface old photographs and past moments on this day features archived stories, throwback posts, frequently trigger nostalgia. But whether this digital nostalgia improves well-being is unclear. Some studies suggest that viewing old photos online can evoke positive affect and feelings of connection. Others find that it can increase social comparison, envy, or a sense of loss, especially if the past depicted seems happier than the present. The medium matters. 2. Scrolling alone on a phone at night is a very different context from sharing a photo album with a friend. Digital nostalgia is nostalgia without a container. And without a container, the emotion is free to drift in any direction. Perhaps tonight, the screen can rest, and the memories, if they come, can come on their own terms. Some nights nostalgia is a blanket. Some nights it is a cold window. Both are real. There is no correct way to experience nostalgia. On some nights, a memory of a loved one feels like being wrapped in warmth, a reminder that you have been cherished, that softness has existed in your life. On other nights, the same memory feels like standing in front of a cold window, seeing what is outside, but unable to reach it. Both responses are real, both are valid, and neither needs to be fixed. The brain is doing what brains do, responding to context, to chemistry, to the shape of the night. If nostalgia feels warm tonight, let it warm you. If it feels cold, let it be cold. And know that the cold does not mean the warmth was never there. Whenever you are ready, let the belly settle, soft and still, like a lake at dusk. Being listened to while recalling a memory can change how that memory feels afterward. The social context of remembering matters. When someone listens with empathy while you share a memory, the experience of recalling that memory can shift. Studies in social cognition suggest that empathic listening activates reward-related neural pathways in the speaker, creating a subtle positive association with the memory being shared. The memory is being reconsolidated in the presence of warmth, and that warmth may become part of the memory itself. Conversely, sharing a memory with someone who dismisses or judges, it can make the memory feel harder, more defended. The listener shapes the memory without knowing it. Perhaps that is why telling an old story to the right person can make the story feel new, not changed, but held in kinderhands. Empathic listening may gently activate reward pathways, making the memory warmer. Neuroscience research on social interaction has shown that being listened to with genuine attention activates regions associated with reward and social bonding, including the ventral striatum and medial prefrontal cortex. When this activation occurs during memory recall, it may create a positive association that gets incorporated into the memory during reconsolidation. The result is not a fabrication. The memory is still true, but it has been gently warmed by the experience of sharing it. This is one of the mechanisms by which therapy, conversation, and simply being heard can change the way old memories feel. The memory does not need to be rewritten. It needs to be witnessed. And sometimes, being witnessed is enough to turn a cold memory warm, like sunlight falling across a stone that has been in shadow. Collective nostalgia, shared by a group, tends to deepen social bonds. When groups reminisce together about a shared era, a shared event, a shared struggle, the resulting emotion strengthens the bonds between them. This is called collective nostalgia, and it has been studied in the context of national identity, organizational culture, and close relationships. Shared remembering creates a sense of we, a feeling that the past belongs to the group, not just to any one person. This collective ownership of memory fosters trust, loyalty, and a sense of continuity. It is one of the oldest forms of human connection, sitting in a circle, telling stories about what happened, and feeling that the telling makes the group more whole. The stories we share do not just preserve the past, they weave the present together, thread by quiet thread. Telling stories about the past is one of the oldest things humans do together. Long before writing, before libraries, before any technology of preservation, humans told stories. Around fires, in shelters, on long walks, the past was kept alive through speech. Oral traditions served not only to transmit knowledge, but to bind communities together through shared narrative. Every culture has its storytelling rituals, and many of them center on the past. Origin stories, ancestrales, accounts of hardship and survival. The act of telling is itself a form of memory consolidation. External, social, and profoundly human. When you tell someone about your day, you are participating in a tradition as old as language itself. And tonight, in a sense, that is what this is. A quiet voice telling stories about old memories, keeping you company until the fire burns low. Children learn to shape their memories through conversations with caregivers. Scaffolded, remembering. Young children do not remember on their own the way adults do. They learn to remember through interaction, a process developmental psychologists call scaffolded remembering. When a caregiver asks a child, "What did we do at the park today?" and helps the child organize the answer, the child is learning not just what happened, but how to structure a memory. Over time, these conversations teach children to create coherent narratives of their experiences. The quality of this scaffolding matters. Children whose caregivers engage in elaborative, reminiscing, asking open-ended questions, adding detail, validating feelings, tend to develop richer autobiographical memories. Memory, in its earliest form, is a conversation someone once helped you remember, and perhaps, without knowing it, you have helped someone else remember. 2. Collaborative recall. Two people remembering together often produces a richer Version. When two people recall a shared experience together, the result is often different from either person's individual memory. Each person contributes details the other has forgotten, fills in gaps, corrects misrememberings, and adds emotional texture. The collaborative version is not always more accurate. Groups can reinforce errors, too, but it is typically more complete and more emotionally nuanced. There is something inherently softening about remembering with someone else. The shared act of recall distributes the emotional weight. No one carries the whole memory alone. And in the telling, the memory often becomes gentler, as if the act of sharing it sands down its rougher edges. Two people, one memory, and a version that is kinder than either could have made alone. Narrating a memory is itself a form of reconsolidation. You edit it gently with each telling. Every time you tell a story about your past, you are not merely retrieving a memory. You are reconsolidating it. The act of putting experience into words requires selection. Which details to include, which to leave out, which feelings to emphasize. These narrative choices subtly reshape the memory each time it is told. Over many tellings, the memory becomes more story and less raw experience. The edges smooth, the language settles, the emotional tone may shift toward acceptance or meaning-making. This is not distortion. It is narrative shaping, one of the brain's most elegant forms of emotional regulation. You might let the feet grow heavy now, warm and still, like two quiet stones at the bottom of a stream. Each telling is a draft, and perhaps tonight's draft is the softest one yet. Bedtime stories may be shared, memory rituals, connecting generations through gentle repetition. The bedtime story is one of the most universal rituals of childhood. A caregiver sits beside a child, tells a story, and the child drifts towards sleep. The content of the story matters less than the ritual itself, the presence, the voice, the rhythm of language at the edge of sleep. Some researchers have suggested that bedtime stories function as a form of shared memory practice, a nightly rehearsal of narrative, companionship, and the gentle transition from waking to sleeping. The stories become part of the child's emotional landscape, associated with safety, warmth, and the sound of someone who cared enough to stay. And perhaps tonight, this voice is something like that, a story told at the edge of sleep, for no reason other than to keep you gentle company. Forgetting is not a flaw. It is an active process that keeps the brain efficient. We tend to think of forgetting as failure, a sign that the brain has lost something it should have kept. But neuroscience suggests otherwise. Forgetting is, in many cases, an active and adaptive process. The brain selectively weakens synaptic connections that are no longer useful, clearing cognitive clutter and making room for new learning. This process, sometimes called adaptive forgetting, ensures that the brain remains flexible and responsive rather than overloaded with outdated information. Without forgetting, every trivial detail would compete with every meaningful one. The brain would be crowded, noisy, unable to prioritize. Forgetting is not the opposite of remembering. It is its quiet partner, making sure the library has room to breathe. During sleep, the brain prunes synaptic connections, clearing space for what comes next. The synaptic homeostasis hypothesis, proposed by Giulio Tononi and Chiara Cirelli, suggests that during waking hours, synaptic connections throughout the brain are strengthened by learning and experience. By the end of the day, the brain is saturated, synaptic strength is high, energy consumption is elevated, and the capacity for new learning is reduced. Sleep, particularly slow-wave sleep, is proposed to restore the balance by downscaling synaptic strength across the board. The strongest connections, those associated with meaningful memories, survive the pruning. The weaker ones are allowed to fade. The result is a brain that wakes refreshed, with signal preserved and noise removed. The gardener does not keep every seedling. The garden thrives because some things are let go. The brain can intentionally downregulate unwanted memories, a quiet act of self-care. Beyond passive forgetting, the brain has mechanisms for actively suppressing memories that are unwanted or intrusive. The prefrontal cortex can inhibit hippocampal retrieval, effectively dampening the activation of a memory trace. This process, sometimes called retrieval suppression, has been demonstrated in paradigms like the think-no-think task. where participants learn to suppress specific memories on cue. Over time, suppressed memories become harder to retrieve, not erased, but muted. This capacity is not limitless, and it is not effortless, but it speaks to something reassuring. The brain is not a passive vessel. It has tools for managing what it holds. Perhaps the eyelids can grow heavier now, a gentle closing, like the last page of a long and tender book. The brain does not merely remember, it also chooses, gently, what to set aside. Some forgetting is adaptive. It helps us update beliefs that no longer serve. Not all forgetting is loss. Some of it is refinement. When you learn that an old belief was wrong, that a road has changed, that a friend has moved, that a fact you memorized was inaccurate, the brain needs to weaken the old trace to make room for the updated one. This process, called proactive interference resolution, is a form of adaptive forgetting. Without it, outdated information would compete with current knowledge, creating confusion and indecision. The brain is not clinging to everything it has ever known. It is continually curating, keeping what is relevant, letting what is outdated recede into the background. Letting go of what no longer fits is not weakness. It is the quiet intelligence of a mind that is still growing. The fading affect bias means negative feelings fade faster than positive ones. The brain protects the good. Across many studies, researchers have observed a consistent pattern. The emotional intensity of negative memories fades more quickly over time than the intensity of positive ones. This is called the fading affect bias. It means that over the years, the pain of a bad experience tends to soften faster than the joy of a good one. The brain is not erasing the negative memory. It is simply allowing its emotional charge to diminish more rapidly. The result is a memory landscape that gradually tilts toward the positive, not because the brain is lying, but because it is selectively maintaining what nourishes. The ache fades a little faster than the warmth, and perhaps that is one of the quietest kindnesses the brain offers, a bias toward holding what is good. Over time, most memories become gist-based. We keep the meaning, release the details. As memories age, they undergo a transformation. The specific details, the exact words spoken, the precise color of a room, the order of events, gradually fade. What remains is the gist, the general sense of what happened, the emotional tone, the meaning. This shift from detail to gist is not a failure of the system. It is a feature. Gist-based memories are more flexible, more transferable to new situations, and more resistant to interference. They allow you to carry the essence of an experience without the burden of every particular. The brain keeps what matters and releases what weighs it down. Like a letter read so many times that the words have blurred, but the feeling is still perfectly clear. The reminiscence bump suggests that identity-forming memories resist fading. They are shelved with care. While most memories fade with time, those from the reminiscence bump period, roughly ages 15 to 25, tend to persist with unusual clarity and accessibility. These are the memories that defined who you became, the choices, the discoveries, the first times. They are encoded with stronger emotional valence, rehearsed more frequently, and integrated more deeply into the life narrative. They resist the natural process of fading because they are central to the self-story. They are not just memories. They are the chapters that hold the plot together. The brain gives them extra protection, extra rehearsal, extra shelf space. The memories that made you who you are, the brain keeps them close. The way you might keep a favorite book within arm's reach. Perhaps the gentlest truth about memory is this: what fades was never truly lost. It simply softened. Memory is not a vault. It is a living process, one that softens, reshapes, and distills over time. The details you cannot recall are not failures of the system. They are evidence that the system is working, keeping the meaning, releasing the noise, making room for what comes next. The brain does not hold on to everything because it does not need to. What it keeps is what matters: the feeling of a hand in yours, the sound of a voice you loved, the sense that you were, for a moment, exactly where you were meant to be. Everything else is allowed to soften, like light fading at the edge of a long, warm day. If you would like, let the whole body settle now, every part resting, every part held. What fades was never truly lost. It simply became part of you in a quieter way. And so we come to the end of the shelves. For tonight, the night library never closes. It has been here longer than language, longer than names, longer than the first story anyone ever told beneath a sky. And every time you sleep, the quiet librarians return to their work, not to erase, but to soften, to reshelve, to make room for whatever tomorrow brings. You do not need to hold on to any of this. The facts, the names, the rhythms and ripples, they were never meant to be memorized. They were only meant to keep you company for a while. The way a friend might sit beside you and talk quietly about nothing in particular until your eyes close. Perhaps your whole body can feel like a book returned to its shelf, resting, still, belonging exactly where it is. If you are still awake, that is perfectly fine. The library is patient. The shelves are not going anywhere. And the next time you close your eyes, the slow waves will begin again. The ripples will return, and the spindles will hum their quiet chime. All of it happening without any effort from you at all. Sleep well tonight. The library is in good hands.